In this lecture, we will talk about unitary evolution. Now suppose we want to apply some operation on a quantum state. Quantum mechanics only allows linear operations in the compact vector space to be applied to quantum states. And recall that from the previous lectures, we know that a vector space is a set V on which vector addition and complex scalar multiplication can be applied. Therefore, we can represent the operation using a matrix U, and we may apply some operation U at some time on the quantum state. Let's say the initial state is psi 0, and then at time t, we apply an operation U on the quantum state to obtain a transformed state, which is denoted by psi t. So what properties U should have in order to satisfy under this formula? So what are the postulates? That is, first, information is conserved if measurement is not made. Suppose you start with two states which are observably different. Then both of them evolve and they will stay orthogonal. This means that they must be different and distinguishable. And the inner product is unchanged by time, and orthogonal vectors remain orthogonal. So what does it mean by having the inner product remains unchanged by time? Suppose we have a phi state and then apply U to obtain ut phi. And in another state, which is psi, we also apply ut and then obtain ut psi. The inner product of the initial state, phi and psi, is denoted by this, and the inner product of the final state is denoted by this. And then inner product remains unchanged by time means that they should be equal. This implies U dagger U is an identity matrix. So what kind of properties that U have? That is U dagger U equal to identity. And U is always invertible, and the inverse of U is U dagger. And the inverse of U is also a unitary operation, meaning that if we have a quantum state psi and apply U, and then we obtain U psi, and then we further apply the inverse of U, which is also a unitary operation. After that, we obtain inverse of U multiplied by U on psi, which gives us psi. This means that we can always undo the action of U and nothing is lost in the process, and this is called reversible computing.